We're continuing talking about Bayes' theorem. I want to provide a few additional examples beyond what are given in the textbook. The first of these is just a little bit talking about how Bayes' theorem can be related to problems, or used in problems related to inferring from noisy measurements. So this is a formalism that comes up a lot in signal processing and signal estimation, which is something that is near and dear to my heart. So I'm just going to share it with you. So the idea here is we want to think about inference from noisy measurements. If you're an electronic engineer, you know anytime you have a sensor, that sensor is measuring something about the world, but it's not, of course, a perfect measurement. There is various sources of noise that can come into that measurement. So this, in a very generic setting, we're going to say, okay, if we have X is something that we're observing about the world, this is the real property that we're observing in the world. So maybe this is the level of water in a tank. This could be a set of image pixel measurements if we're taking from a digital camera. Anytime you have anything that you're sensing, you can think of this in this way. And we can set Y to be the observation, which is often noisy. We can think of P of Y given X. This is saying if X was had a particular value, then the probability P of Y given X is the probability that the sensor produces a particular observation Y given X. So you'd like this to be 1 when Y is equal to X and 0 if Y is not equal to X. And that would be true if you had a perfectly noiseless sensor. But if you have a noisy sensor, this could have some distribution. And this can be thought of as a model for the noisy measurement. And then Bayes' theorem says, well, okay. If I just write out Bayes' theorem, it's going to be this. So we have this statement that you can think of sensing the world as saying, I want to infer something about the true nature of the world based on some observation of it. If my observation process is not pristine but has noise in it, then there may be some uncertainty about what the true nature of the world is, even after I observe it. And that's captured by this probability distribution, to say the probability of the true thing conditioned on my observation. So this is like saying, well, if I take a depth measurement of a tank, and I measure it as 20 meters, but maybe the true height of the tank could be something different. But if I have this distribution, this is describing that uncertainty. And Bayes' theorem says we can write it this way. I'm just writing down Bayes' theorem. So this is P of Y given X. That is saying, okay, if X was this value, that's what the probability that my sensor would produce that particular value. So that's modeling the sensor. And then we have this thing of P of X. So what is P of X here? This is the probability of X. So this is the prior or unconditional probability that this thing in the world, of this particular thing in the world that we're measuring having this particular value. So this, I'm just going to introduce this notation. This is often referred to as a prior probability distribution. So one interpretation of sensing the world in a Bayesian framework is to say, well, things in the world are random and they have some distribution, And if you can model that distribution P of x, then when you make a measurement of something in the world, you can then cook up this probability of the thing in the world having that particular value conditioned on the observation that you made. And I'm not going to go too much further with this now. I would love to return to this and develop it further towards the end of the class, using some examples from signal processing and signal denoising, and hopefully we'll have time to do that, but we'll see about that. Okay, the other example I wanted to go into that illustrates an important idea from Bayes' theorem is an example taken from medical, or related to medical diagnostic. So I'll use this for now. So I'm going to discuss some issues that are related to probabilities of how effective medical screening can be. So I'm going to talk about the probabilities related to a mammogram. So mammogram is a X-ray of a woman's breast. It's a test for breast cancer. Medical tests are not noise-free. So what I mean by that is anytime you have a medical test, there's possibility that the test could have error. So it can have false positive error or false negative error. And that error is described probabilistically by so-called sensitivity and specificity of the test. So I looked up these values for sensitivity and specificity for mammogram, and I looked these values up from the National Cancer Institute website, so they're at least not totally bogus. So these are usually often given in terms of percent, but I've converted them just to probability. So a sensitivity of 0.85 and a specificity of 0.9. So what these mean, I didn't define these, but sensitivity is if a person has the particular disease that the test is testing for, then the sensitivity is the probability that the test will give a positive result given that the person has the disease. So I can describe the sensitivity here as this is the probability of a woman getting a positive test result given that she has cancer, given that she has breast cancer. So this says if somebody with breast cancer goes and gets a mammogram, then there's an 85% chance that they'll get a positive result on that mammogram and a 15% chance that she'll get a negative result on that mammogram. The specificity is another measure of the properties of the test. And this says, what's the probability of getting a negative test result if the person does not have the disease? So in this case, 0.9 is the probability that the test is negative given that the patient does not have breast cancer. Okay, so I'm not trying to be controversial or anything here. If you follow the news recently, in the past couple of years, every now and then guidelines for which women should get mammograms and which shouldn't change, and this is often very controversial because some people get very upset when they say if the recommendation changes to have fewer people screened. I'm not trying to be controversial or anything here. I just am wanting to describe some of the underlying mathematics that goes into thinking related to making that kind of recommendation. So the basic reason why one might not want to over-screen for medical tests is that if you screen too many people, then you're going to be producing a lot of false positive results, which has negative consequences because it's upsetting, and it can lead women to incur further cost or further medical risk if they do surgery or whatnot. And of course, all of this is not specific to mammogram. I chose it as an example. So one other piece that's relevant to this is the overall prevalence of the disease among a given population. So again, these are numbers that I've chosen from the American Cancer Institute. And what these numbers are is the chance of a woman at a given age of developing breast cancer within the next 10 years. So for a woman at age 30, she has a 0.44% chance of developing cancer in the next 10 years. A woman that has of age 60 has a 3.56% chance of developing cancer in the next 10 years. So what I want to do is I'm going to abuse these a little bit. I'm going to take this as sort of a stand-in for the probability that a given person has breast cancer. So I'm going to say, well, all right, if breast cancer is 0.44% of the population has breast cancer of people age 30, and 3.56% of the population of women who are age 60 have breast cancer, then what can we say? How can we do something with Bayes' theorem to interpret test results? So, and I'm just explaining where these numbers come from. This is probably an underestimate because this is the number for people who get it within 10 years. It's not necessarily the number of people who have it right now. So be that in may. The mathematics of what I'm going to say are equivalent, but that number, just that's where it came from. Okay, so an important question is, if a given person goes into the doctor's office and has a mammogram and they test positive, I can ask the question, what is the probability that that person actually has cancer? Now that may seem silly because, well, if they test positive, they have cancer, right? Not necessarily, because the test is not 100% sensitive and it's not 100% specific. So, the question is, 30-year-old woman positive mammogram. What is the chance that she has cancer? So you might naively think it's going to be like 85 or 90% because that's how sensitive or specific the tests are. But watch what happens when we actually look at this through Bayes' theorem. So we can think of this as a conditional probability. So what we're asking here is, what's the probability that this woman has cancer given that she has a positive test result? The way we can use knowledge about the test properties is through the test sensitivity and specificity. So these are statements about what's the probability of testing positive or testing negative given the presence of cancer or not. So what we can do is we can think of the event she has cancer or she does not have cancer as being like our A1 or A2 that partition the space, and we can write this out. So this we want to flip this around by Bayes' theorem. this tells us that Bayes' theorem tells us we can write this as this is the probability of I should write this as test pos to be consistent there. The probability that she tests positive, given that she has cancer, times the probability that she has cancer over this. Sorry, I'm running out of space on the board here. Oh, so no. I started to write the wrong thing. Let me write this carefully. So we're splitting over the event she has cancer. So in the numerator, it's she tests positive given cancer. So in the denominator, when we normalize this is going to be the probability that she tests positive given that she has cancer times the probability she has cancer plus the same thing, but where we go to the other outcomes of not having cancer. So it's this. Okay. So this probability of testing positive, given that she has cancer, that's exactly the sensitivity of the mammogram. So that's 0.85. This, the probability that she has cancer, this is where the patient's general risk enters into the picture. So the unconditional probability that she has cancer is just like, before you know anything about that test result, what's the probability that this person has cancer? So you can model this by, you could include other risk factors other than age, but the primary one is age. So you can just say, well, okay, among all 30-year-old women, what's the prevalence of breast cancer? And I'm taking this data to say it's 0.44%. So this is 0.85 times 0.0044. And then down here, probability to test positive given cancer, that's the same thing. Plus, and then the probability of testing positive given that you do not have cancer. So that is not the specificity, but it's 1 minus the specificity. Because the only test results are, in this case, are positive or negative. So the probability of testing positive given no cancer is going to be 1 minus the probability of testing negative given no cancer. So that's going to be 0.1 times probability of not having cancer, which is 1 minus 0.0044. Okay. So when I computed this out, I got 0.036, which is 3.6%. So if a woman with no other risk factors other than has a mammogram and it turns up positive, obviously this is greatly going to distress her, but she only has a 3.6% chance of actually having cancer. This is a lot lower than most people's intuitive gut feeling for what the chance would actually be. And the reason is that it includes the prevalence in the general population, which is low. If we redo this for the 60-year-old, we can do exactly the same calculation, and I get probability of her having cancer given a positive test result. It's the same structure, but instead of the only thing that changes for her is the unconditional probability of her having cancer, which would be 3.56% with this data that I'm using. So I get 0.85 times 0.0356, 0.85, 0.0356 plus 0.1 times 1 minus 0.0356. And when I compute this out, this is 0.238. So the point here is that the only difference between these two women is the general risk of that population. In one case, you'd say that after a positive test result, she has a 3.6% chance of having the disease. In this other case, after the same test result, you'd conclude she has a 23.8% chance of having the disease. So there's obviously a lot more to it than just this, but this is an illustration of the point that, is part the kind of reasoning that goes through thinking about whether or not broad-based screening for a particular disease is appropriate. And obviously, I mean, that's a larger public health, public policy question. But this is the kind of mathematics that you can use to inform that.